A combustible mixture is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. In the previous video, Flame on Torch, we gave the definitions and foundation for combustion reactions. In this video, a combustible mixture, we'll do some sample combustion calculations. The given problem statement may seem simple, but it's going to take us quite a while to get through the solution. 2 kmols per second of propane are burned in 25% excess dry air in a faulty combustor. 100% of the hydrogen combusts to form water, but only 80% of the carbon combusts completely to carbon dioxide. The remainder combusts to carbon monoxide. You can see that the combustor is faulty because we are only getting 80% CO2 and 20% CO. The things to calculate are A. The molar flow rate of air into the combustor. B. The molar flow rate of each of the combustion products. C. The molar flow rate of the exhaust. D. Report the composition of the exhaust on both a wet and a dry basis. To solve this problem, we are going to have to set up the chemical equations for the combustion. There are many different sets of chemical equations that we could write. We'll consider 2 sets here, but there are many others. In the first, propane plus 5 oxygen goes to 3 carbon dioxides plus 4 waters. We'll call this equation 1. The second equation is propane plus 7/2 oxygen goes to 3 carbon monoxide plus 4 waters. We'll refer to this as equation 2. The other set of equations we're going to look at is propane plus 7/2 oxygen goes to 3 carbon monoxides plus 4 waters, and we're calling this equation 3. I know it looks just like the equation 2, but calling it equation 3 will make it a little cleaner when we're writing things down. And the second equation in the second set is carbon monoxide plus 1/2 oxygen goes to carbon dioxide, equation 4. It's worth checking to see if we have the expected combustion products. Set 1 gives us carbon dioxide, water, and carbon monoxide. Set 2 gives us carbon monoxide, water, and carbon dioxide. So we have all the species that we're generating in either case. We should also check to make sure that they're linearly independent. In the first set, carbon dioxide only appears in equation 1, and carbon monoxide only appears in equation 2. So we can't linearly combine them to eliminate one of the equations. In the second set, propane only appears in equation 3, and carbon dioxide in equation 4. So we can't linearly combine them to eliminate one of the equations. In order to solve the problem, we are going to have to calculate the excess air, so we need to calculate the stoichiometric or the theoretical air. I hope it won't be too confusing if I intermix stoichiometric and theoretical in this set of calculations. First, the stoichiometric flow rate of oxygen is going to equal the ratios of the stoichiometric coefficients of oxygen and propane times the flow rate of the propane. Substituting in, we get -5 over -1 times 2 kmols per second, which gives us the stoichiometric flow rate of oxygen is 10 kmols per second. The fraction excess is 25%, which is equal to the oxygen in minus the stoichiometric or theoretical oxygen over the theoretical oxygen. Rearranging, we get that the total oxygen in is going to be 1 plus the fractional excess times the stoichiometric oxygen, which is 1.25 times 10 kmols per second, or 12.5 kmols per second. That is the flow rate in of oxygen for either set of equations. To get the theoretical air, we also need the flow of nitrogen, and as we discussed before, the flow rate of nitrogen is 79/21 the flow rate of oxygen, so that gives us 47 kmols per second of nitrogen. The total airflow rate requested in part A is the sum of oxygen and nitrogen, which is 12.5 plus 47, or 59.5 kmols per second. At this point, we are going to go through the full set of mole balance equations that we got from the chemical reactor with multiple reactions. If you recall, that's the flow rate of species I out is equal to the flow rate of species I in, plus the sum of the stoichiometric coefficients of species I in reaction to J times the extent of reaction J. So that's what we're doing here. First, for propane, we have the propane out equals the propane in minus extent 1 minus extent 2. Since we know that there's no propane coming out, we get that extent 1 plus extent 2 equals 2 kmols per second. The CO2 out equals the CO2 in plus 3 extent 1 plus 0 extent 2, which we can rearrange to say the moles of CO2 out equals 3 times extent 1. The CO out equals the CO in plus 0 times extent 1 plus 3 times extent 2, which we can rearrange to give us the moles of CO out is 3 times extent 2. The moles of oxygen out are the moles of oxygen in minus 5 extent 1 minus 3.5 extent 2, which is 12.5 kmols per second minus 5 extent 1 minus 3.5 extent 2. The moles of nitrogen out is the moles of nitrogen in, and since its stoichiometric coefficient is 0, being an inert, we get 47 kmols per second coming out, our first answer to part B. The moles of water coming out equal the moles of water coming in, which was 0 by the way, since it's dry air, plus 4 extent 1 plus 4 extent 2, so that the molar flow of water out is equal to 4 extent 1 plus 4 extent 2. For those who are counting, that's 5 equations and 6 unknowns. We need one more equation. Now we'll apply the constraint that 80% of the propane goes to CO2 and 20% of the propane goes to CO. That gives us the final equation. The ratio of CO out to CO2 out is equal to 1 minus 80% over 80%, which is a fourth, or 0.25. And substituting in the mole balances is equal to extent 2 over extent 1. We also know that extent 1 plus extent 2 equals 2 kilomoles per second, so we can substitute that extent 2 equals 1/4 of extent 1, and that gives us that extent 1 is 1.6 kilomoles per second, and then substituting back, extent 2 equals 0.4 kilomoles per second. Now that we know the two extents, we can solve for the remaining answers to part B. The CO2 out is 3 times 1.6, or 4.8 kilomoles per second. The CO out is 3 times 0.4, or 1.2 kilomoles per second. The moles of oxygen out is going to be 12.5 minus 5 times 1.6 minus 3.5 times 0.4, which equals 3.1 kilomoles per second. And the water coming out is going to be 4 times each of the two extents. That comes out to be 8 kilomoles per second. To get the dry and wet compositions, we are going to divide the individual species molar flow rates by either the sum of the species molar flow rates minus the water flow rate, or by the sum of the species molar flow rates. So in equation form, the mole fraction of species I dry is equal to the molar flow rate of species I divided by the sum of all the molar flow rates minus the molar flow rate of water. For the wet composition, we have the same expression, but without the minus molar flow rate of water. I'm not going to explicitly do the tedious substitutions. We will just do it in a spreadsheet because there are an awful lot of these equations. Here's the promised spreadsheet. Handbook or reference values are in blue. Problem parameters are in green. The link to the actual spreadsheet is on the video reference page. We entered the ratio of nitrogen to oxygen as 79/21. The flow rate for propane in is given as 2 kilomoles per second. The percent excess air is 25%, and the percent carbon to carbon dioxide conversion is 80%. You can see the stoichiometric coefficients in the two columns for the two reactions. We have the columns for the molar flows in and the molar flows out. The flows out were calculated from the flows in and the extents. We just have to enter one formula and drag it down for all of the outflows. Then we've calculated the compositions in and out on both a dry basis and a wet basis. We just have to enter the formula for the dry basis once and the wet basis once, and we can drag fill the others. As usual, the answers are bolded. We will solve the problem again using equations 3 and 4 instead of equations 1 and 2. The set of equations is different, but we should end up with the same results for the flows and compositions. Again, starting with the mole balance equations for multiple reactions, we have the propane out equals the propane in minus extent 3, and that gives us extent 3 is 2 kilomoles per second. The CO2 out is equal to the CO2 in plus extent 4. That gives us the moles of CO2 out is equal to extent 4. The CO out equals the CO in plus 3 extent 3 minus extent 4, which gives us that the CO out is equal to 6 minus extent 4. The oxygen out equals the oxygen in minus 3.5 extent 3 minus 0.5 extent 4, which simplifies to 5.5 minus 0.5 extent 4. The moles of nitrogen out is the moles of nitrogen in, which hasn't changed and is still 47. And the water out is equal to the water in, which is 0 plus 4 extent 3, which equals 8 kilomoles per second, which was what we got before. As before, we can use our CO2 to CO constraint to determine the extent of reaction 4, which results in extent 4 is 4.8 kilomoles per second. The moles of CO out is 1.2 kilomoles per second. The moles of oxygen out is 3.1 kilomoles per second. The moles of water out is 8 kilomoles per second. Here's the complete spreadsheet. The main differences are that we had to include stoichiometric coefficients for equation 1 because they're needed for calculating theoretical and excess air. In addition, the stoichiometric coefficients for reactions 3 and 4 differ from those from reactions 1 and 2, and the extents of the reaction are different. Otherwise, the answers come out exactly the same. Both of these spreadsheets are on the webpage for the video for you to peruse and see how we did these calculations. The takeaways are: 1. Choose a linearly independent consistent set of chemical equations that involve all reacting species. 2. The mole balance equations using the extents of a reaction are usually valuable. 3. Know how to calculate excess air or excess fuel. 4. Spreadsheets are useful for keeping track of everything. Thanks for watching. This video is brought to you by the DOFPro team.